The most distant object human beings have ever photographed is a smudge, a faint, red smudge against a field of black. It formed 290 million years after the Big Bang, in a universe so young and so different from our own that the physics we use to describe the cosmos today barely apply. The light from that smudge left its source more than 13 billion years ago. By the time it reached us, the universe had expanded so dramatically that the galaxy itself is now tens of billions of light years away. We cannot visit it. We cannot send a signal to it. We can only look at what it was, not what it is. The James Webb Space Telescope found it. Webb launched on Christmas Day 2021, and for 6 months, engineers held their breath. 1,044 separate mechanisms had to function without a single failure. The telescope's primary mirror, composed of 18 gold-coated hexagonal segments made from a metal called beryllium, had to unfold in deep space with perfect precision. The sunshield, a 5-layered structure the size of a tennis court, had to deploy correctly. Each layer had to separate and tension properly, because a failure at any stage would have ended the mission before it began. Every mechanism worked. Every hinge turned. Every panel locked into place. Then Webb opened its eye and looked back further into time than any instrument ever built by human hands. Webb does not orbit Earth the way the Hubble Space Telescope does. Instead, it circles a point in space called the second Lagrange point, located approximately 1 million miles from Earth in the direction away from the Sun. At this location, the gravitational pulls of Earth and the Sun combine in a way that keeps the telescope in a stable position relative to Earth as both orbit the Sun together. This orbit keeps Webb on the permanent night side of Earth, shielded from the Sun's light, heat, and radiation. The sunshield blocks solar energy so effectively that the side facing the Sun reaches temperatures approaching 85 degrees Celsius, while the opposite side, where the instruments sit, cools to approximately -233 degrees Celsius. That extreme cold is not a side effect. It is a requirement. Webb is an infrared telescope. It detects light that human eyes cannot see, light with wavelengths longer than visible red. The reason Webb must observe in infrared comes down to a fundamental property of the expanding universe. When a galaxy exists in the early cosmos, the light it emits is ultraviolet and visible, the bright blue output of young, hot stars forming at prodigious rates. But as that light travels across billions of light years of expanding space, the space itself stretches, and the light stretches with it. Wavelengths grow longer. Visible blue becomes visible red. Visible red becomes near infrared. An ancient ultraviolet from a galaxy formed just a few hundred million years after the Big Bang arrives at our detectors as deep infrared. Webb sees it. Earlier telescopes, including Hubble, could not. Hubble's instruments were optimized for visible light and went blind at precisely the distances where the most ancient galaxies hide. Webb does not simply see farther, it sees earlier. When astronomers say a galaxy is 13.5 billion light-years away, they mean the light took 13.5 billion years to travel from that galaxy to our detectors. The galaxy we see is not the galaxy as it exists today. It is the galaxy as it existed more than 13 billion years ago, a snapshot frozen in ancient light. Webb extends this principle to its absolute limit, capturing photons that began their journey when the universe was less than 5% of its current age. These photons carry information about a cosmos so young that most of the structures we recognize today did not yet exist. There were no solar systems. There were no planets. There were no elements heavier than lithium in any meaningful abundance. There was only gas, dark matter, and the slow accumulation of gravity-pulling structure out of an almost uniform void. And yet what Webb found when it looked into that void defied nearly every prediction cosmologists had made. The galaxy designated JADES-GSZ 14-0, which researchers have come to call by the shorthand JADES, set the distance record when spectroscopic analysis confirmed a redshift of 14.32. That number means the light has been stretched by a factor of 15 during its journey. Ultraviolet photons emitted when this galaxy was actively forming stars arrived at Webb as deep infrared radiation after traveling for more than 13 billion years. This galaxy formed 290 million years after the Big Bang, when the universe was only 2% of its current age. Scientists expected to find something small, something faint, irregular, and primitive. Models of galaxy formation predicted that early galaxies would be tiny clumps of matter, dim and chaotic, just beginning the slow process of assembling structure. Simulations ran on the world's most powerful computers consistently showed that the early universe should be dominated by small, relatively dim objects. The conditions for building large, luminous galaxies required time. Gravity had to pull material together. Stars had to ignite, live, die, and scatter heavy elements into the surrounding gas. New generations of stars had to form from that enriched material. All of this takes time. The universe at 2% of its current age simply should not have had enough time. Jades is not small or dim. It spans more than 1,600 light-years in diameter. It glows with the light of stars forming at a rate dozens of times higher than the current star formation rate of the entire Milky Way. It is so luminous that Webb could have detected it even if it were 10 times fainter. One astronomer described the discovery as finding a fully grown adult where the models predicted a newborn infant. Another said, with no exaggeration, that it might break cosmology. And Jades was not alone. Webb's first deep-field images showed dozens of early galaxies that were too large, too bright, and too structurally organized for their age. Every new observation confirmed the same pattern. The universe's earliest galaxies were more extreme than any model had predicted. Some researchers proposed that galaxy formation simply happened faster in the early universe, that stars formed more efficiently from primitive gas, or that dark matter halos collapsed more rapidly under conditions that no longer exist. These ideas help, but they do not fully close the gap between observation and theory. The galaxies remain too extreme. One proposed explanation involves the initial conditions of the Big Bang itself. Perhaps matter did not spread entirely uniformly in those first moments. If certain regions began slightly denser than average, gravity would have pulled more material into those regions more quickly, allowing galaxies to assemble faster there. But this raises its own questions. What created those dense regions? What physics generated those initial density fluctuations at higher amplitudes than standard models predict? The discovery of early galaxies like Jades extended humanity's observational reach into cosmic history by 40% within just 18 months of Webb's first science operations. Each new galaxy found at extreme distances adds another piece to a puzzle that refuses to fit together using the tools we had before. And then Webb found something that made the galaxy formation problem look simple. In the modern universe, there is a ratio. For every 10,000 solar masses of stars in a galaxy, there is roughly one solar mass in the central black hole. The Milky Way follows this ratio. Nearby galaxies follow it. Distant galaxies, when astronomers could study them with older telescopes, followed it. The relationship between black hole mass and stellar mass held so consistently across so many different types of galaxies that scientists built entire theoretical frameworks around it. It was treated as a fundamental law of galaxy evolution, an inevitable consequence of black holes and galaxies growing together through billions of years of shared history. Webb looked at a galaxy that existed 570 million years after the Big Bang and measured its black hole mass. The result was impossible under the old framework. The black hole at the center of this galaxy equaled 10% of the total stellar mass of the entire system. For every 10 solar masses of stars, there was one solar mass of black hole. This ratio violated the accepted relationship by a factor of 1,000. Astronomers call objects like this overmassive black holes, a term that barely captures the severity of the anomaly. Imagine if the human heart weighed 1/10 as much as the entire body. That is the proportion Webb was seeing in these early galaxies. The black hole does not just anchor the galaxy at its center, it dominates the entire system. Webb found dozens of these objects. They appear as compact, intensely red points in deep field images, so consistently colored and so uniformly compact that astronomers gave them an informal name: little red dots. The red color comes from hot gas spiraling into the central black hole. As matter accelerates toward the event horizon, friction heats it to millions of degrees. This superheated accretion disk radiates across the electromagnetic spectrum, and heavy dust surrounding the system absorbs shorter wavelengths and re-radiates the energy in the infrared, giving the objects their characteristic crimson appearance. What makes little red dots genuinely confusing is their spectra. When Webb split the light from these objects into its component wavelengths, the resulting pattern showed two completely incompatible signatures simultaneously. Broad emission lines appeared, lines that indicate gas moving at thousands of kilometers per second near an actively feeding black hole. This is a signature astronomers associate with quasars and active galactic nuclei. But the spectra also showed narrow emission lines, signatures of gas moving much more slowly in star-forming regions. Normally, these two patterns come from fundamentally different types of objects. Active nuclei show broad lines. Star-forming galaxies show narrow lines. Little red dots show both at once. No existing category of astronomical object matched what Webb was seeing. Some researchers argued that little red dots are simply heavily dust-obscured quasars. Others suggested they represent a brief transitional phase in galaxy evolution, the moment when a newly formed massive black hole first switches on, while the surrounding galaxy continues forming stars at high rates. A third possibility involves the role of the cosmic environment. Little red dots are not randomly distributed throughout the early universe. They cluster at specific locations in the large-scale web of dark matter and gas that connects all structure in the cosmos. Perhaps their formation requires collisions between gas clouds or interactions between multiple small galaxies that only occur in specific environments. Each spectrum Webb captures adds detail, but no single explanation yet accounts for all their properties. One survey examined 7 little red dots from the same cosmic epoch. All 7 showed the same pattern: overmassive central black holes equal to approximately 10% of their host galaxy's stellar mass. This consistency across independent systems suggests Webb is not seeing random oddities. It is seeing a distinct population of objects that formed through processes not included in current models. And understanding how these black holes got so massive so quickly forces a direct confrontation with the limits of what we know about black hole formation. There are 2 main theories. The first proposes that the earliest black holes formed the same way they form today, from the deaths of massive stars. A star 10 or more times heavier than the Sun exhausts its nuclear fuel, the core collapses, and under the right conditions a black hole forms. This black hole then grows by pulling in nearby gas and merging with other black holes. The problem is time. Even feeding at the maximum physically allowed rate, called the Eddington limit, a stellar mass black hole requires hundreds of millions of years to reach the masses Webb is observing. The early universe simply did not have enough time for that process to produce what Webb is finding. The second theory proposes that some black holes were born large. Instead of forming from the death of a single star, certain massive clouds of primordial gas may have collapsed directly into black holes, bypassing star formation entirely. These so-called direct collapse black holes would begin their lives with masses of thousands to millions of solar masses. They would not need to grow from a small seed. They would start as giants. Webb data increasingly supports this scenario. Several of the overmassive black holes observed appear to be embedded in environments with surprisingly low chemical enrichment, meaning the surrounding gas contains very few heavy elements. Heavy elements accumulate in gas when stars live and die. If very few stars have lived and died in the region surrounding an overmassive black hole, it suggests the black hole did not form after generations of stellar evolution. It formed from pristine gas directly, without ancestors. The implications extend beyond individual black holes. These overmassive black holes are not sitting passively at the centers of their host galaxies. They are feeding furiously, and as they feed, they are reshaping everything around them. Superheated gas spiraling into the event horizon radiates enormous energy outward. This energy pressure drives winds away from the black hole at thousands of kilometers per second, fast enough to escape the galaxy's gravitational pull entirely. Astronomers call this feedback. When a black hole's feedback winds blast through a galaxy, they push star-forming gas out of the system. Without gas, new stars cannot form. The galaxy's growth stalls. This explains why these early galaxies with massive black holes remained so small. The black hole formed first and grew rapidly. As it grew, it generated feedback powerful enough to prevent the surrounding galaxy from building substantial stellar mass. The black hole essentially stunted its own host. Only after the black hole exhausted its available gas supply, quieted down, and allowed the winds to weaken could the galaxy resume forming stars and gradually build its stellar population. Astronomers believe they are catching these systems during that first phase, the phase when the black hole has grown large but the galaxy has not yet had time to catch up. Given another billion years, many of these systems would look far more ordinary. The black hole would still be massive, but the surrounding galaxy would have grown into proportion. Webb also detected the earliest known merger of two supermassive black holes. In a galaxy designated ZS7, which existed 740 million years after the Big Bang, the telescope resolved two distinct bright cores in a single system. Spectroscopic analysis of both cores showed fast-moving gas characteristic of matter falling into black holes. The galaxy contained two supermassive black holes orbiting each other. This was not a chance alignment. Both objects showed signatures of actively feeding black holes in a system that would eventually force them to merge. The two black holes in ZS7 were spiraling inward, losing orbital energy through a process Einstein predicted, but astronomers had never directly observed at this stage: gravitational wave emission from orbiting supermassive black holes. As the two objects circle each other, they emit gravitational waves, ripples in spacetime that carry away orbital energy. Over millions of years, the orbit shrinks. When the two black holes finally merge, the collision will release a burst of gravitational waves powerful enough that future space-based detectors will detect similar events across vast cosmic distances. Current detectors on Earth can detect the mergers of smaller stellar mass black holes in the nearby universe. Observing the merger of supermassive black holes requires a fundamentally different type of detector, one specifically designed to detect lower-frequency gravitational waves from more massive systems. Those detectors are being planned. ZS7 shows us exactly the kind of event they are being built to find. The finding has direct implications for understanding how the supermassive black holes at the centers of modern galaxies, including our own Milky Way, grew to their current sizes. If mergers of supermassive black holes were common in the early universe, they provide an efficient mechanism for rapidly building up black hole mass. A series of mergers between galaxies in the young, dense early cosmos could have accelerated black hole growth dramatically beyond what pure gas accretion could achieve alone. Webb has now found evidence that these mergers were occurring, lending support to the idea that the black holes at the hearts of galaxies today were assembled partly through a series of violent collisions in the cosmic past. While all of this was happening in the distant early universe, Webb was simultaneously teaching us something about the space between stars in our own cosmic neighborhood. In 2025, a pulse of light from a stellar explosion that occurred 350 years ago reached a cloud of interstellar dust and gas. Webb watched the cloud illuminate from within. The light echo it created allowed astronomers to peer inside structures that had previously been invisible. What they found shocked the research team. The interstellar medium was not a diffuse, formless cloud. It was organized into tightly packed sheets, layered like the pages of a book, with features measuring as small as 400 astronomical units across. For scale, the entire orbit of Neptune around the Sun spans only 120 astronomical units. These sheets are several times larger than our entire planetary system, yet they are just small features within much larger clouds. Magnetic fields threading through space likely create these structures. The interstellar medium contains ionized gas, and charged particles respond to magnetic forces. As gas moves through the galaxy, it drags magnetic field lines along, and over time this interaction organizes material into elongated, sheet-like formations aligned with the field. Turbulence generated by supernova explosions, stellar winds, and gravitational instabilities adds complexity, stirring the gas into intricate nested patterns. This discovery matters for understanding star formation. Stars do not form from uniform gas clouds. They form from regions within those clouds where density crosses a threshold, where gravity overcomes the thermal pressure supporting the gas. If the interstellar medium has structured internal organization, with sheets and filaments channeling gas flows, then the locations and rates of star formation depend critically on that organization. Where sheets intersect or compress, conditions may favor the collapse of gas into stellar nurseries. Understanding this structure helps predict not just where stars form, but how efficiently they form and what masses they tend to have. Before Webb, astronomers could only study the outsides of these clouds. The light echo technique gave them a way inside. As the pulse of light from the ancient supernova expands outward, it progressively illuminates more distant material, creating an echo that moves through space and reveals new volumes of interstellar structure. This technique can be applied to any region of space that happens to have a bright transient event, a supernova, a nova eruption, or similar explosion, occurring in a region of interest. Each echo provides a snapshot of a different volume of interstellar space. Combined over many observations, these snapshots could produce a comprehensive map of the three-dimensional architecture of interstellar space across the galaxy. On the 14th of March 2025, a space telescope detected a flash of gamma rays lasting several seconds. Within hours, ground-based observatories around the world swiveled to observe the fading glow. The analysis revealed something extraordinary. This gamma-ray burst had originated when the universe was only 730 million years old. The light had been traveling for more than 13 billion years. Astronomers were watching a massive star explode during the epoch of reionization, the period when the first stars and galaxies were clearing the neutral hydrogen fog that had filled the universe since the cosmic dark ages. Gamma-ray bursts of this type come from the deaths of the most massive stars. When a star more than 20 times heavier than the Sun exhausts its nuclear fuel, the core collapses to form a black hole in less than a second. Material falling toward the black hole forms an accretion disk. Magnetic fields threading the disk launch narrow jets of material perpendicular to the disk plane. These jets punch through the collapsing stellar interior and emerge from the stellar surface at speeds approaching 99.99% of the speed of light. The intense energy heats the jet material to billions of degrees, producing gamma radiation. When one of these jets happens to point in the direction of Earth, our detectors record the burst. The gamma-ray emission is not emitted in all directions. It is beamed. Astronomers only detect bursts whose jets are aimed almost exactly toward us, which means the true rate of these explosions in the early universe is far higher than the detection rate suggests. Webb observed the afterglow of this burst 110 days after the initial detection, by which time the intense gamma-ray flash had faded, and what remained was the slower, dimmer light of the supernova itself. Webb's infrared instruments separated the fatting light of the explosion from the much dimmer glow of its tiny host galaxy. This was technically demanding. The supernova outshone its host galaxy by a significant factor, and both appeared as a single point of light from Earth. Webb's precision made the separation possible. The observations revealed something both comforting and puzzling. This ancient stellar explosion, occurring in a universe that was barely 1 billion years old, looked remarkably similar to supernovae in the modern cosmos. Astronomers compared it to a well-studied nearby supernova from 1998. The brightness, the spectrum, and the way the explosion evolved over time matched closely. The universe at 730 million years old was a radically different environment from today. Stars back then formed from almost pure hydrogen and helium, with essentially no heavy elements to influence their structure or depth. Modern stars form in gas enriched by billions of years of prior stellar evolution, containing carbon, oxygen, iron, and dozens of other elements created by earlier generations of stars. Those heavy elements affect how stars develop, how they burn, and how they die. Yet the ancient supernova died in almost exactly the same way as modern ones. This suggests that the fundamental physics of massive stellar death does not depend strongly on the chemical composition of the progenitor star, or that, for the most massive stars, the mechanism of collapse overwhelms any compositional differences. The host galaxy of this ancient burst was itself revealing. It was small and faint, barely detectable even with Webb's extraordinary sensitivity. This tells astronomers that massive stars capable of producing gamma-ray bursts were forming and dying in some of the smallest galaxies in the early universe. These tiny galaxies were the building blocks of the larger structures we see today. By finding the supernova within such a small system, Webb connected the deaths of the first massive stars to the humble environments in which they lived. Environments that would eventually merge and accrete their way into galaxies like our own. The absorption pattern in the light from this burst also provided a window into the intergalactic medium through which the gamma rays traveled. The burst's light passed through billions of light years of gas on its way to Earth. That gas left absorption fingerprints in the spectrum at specific wavelengths, fingerprints that reveal the composition and ionization state of intergalactic material from 13 billion years ago. The observations detected neutral hydrogen absorption along the line of sight, indicating the burst occurred during or near the tail end of reionization, when pockets of neutral gas still lingered in the cosmic web. Different lines of sight to different gamma-ray bursts will eventually map the patchiness of reionization across the sky in 3 dimensions, revealing how the process unfolded region by region rather than uniformly across the entire universe. Reionization itself is one of the most important phase transitions in cosmic history. After the Big Bang, the universe was hot and filled with ionized plasma. As space expanded and cooled, electrons combined with protons to form neutral hydrogen atoms, and the cosmos became transparent for the first time. But neutral hydrogen efficiently absorbs ultraviolet light, making the universe opaque at the wavelengths that matter most for observing distant objects. This was the cosmic dark ages. No stars existed. No sources of light illuminated the universe. Pure darkness filled all of space for hundreds of millions of years. When the first stars ignited, their ultraviolet output began ionizing the surrounding hydrogen. Bubbles of transparent, ionized gas expanded outward from each star and each galaxy. As star formation accelerated across the universe, these bubbles grew and merged. Within several hundred million years, the neutral hydrogen that had filled all of space had been almost entirely ionized. The universe became transparent again, and light could travel freely across cosmic distances. Webb is designed to observe the galaxy that drove this transformation. One of the key questions about reionization is what powered it. Earlier theories proposed that rare, exotic sources like quasars or a hypothetical first generation of extremely massive stars provided the bulk of the ionizing photons. Webb's observations increasingly point toward a different answer. The early universe contained more bright, star-forming galaxies than any pre-launch model predicted, and many of these galaxies appear to release ionizing photons efficiently into intergalactic space. Measurements of the fraction of ionizing photons that escape galaxies, rather than being absorbed internally, suggest that ordinary star-forming galaxies produced enough ionizing radiation to drive reionization without requiring exotic sources. The universe cleared its own fog using the most common objects it contained. The first stars in the universe were different from anything that exists today. They formed from pristine gas containing only hydrogen, helium, and trace amounts of lithium, the only elements produced in meaningful quantities during the Big Bang itself. No carbon, no oxygen, no silicon, no iron. Without heavy elements to help cool collapsing gas clouds, these clouds remained hot and required far more mass to overcome their internal pressure and collapse into stars. Simulations predict that the first stellar generation, which astronomers call population 3 stars, typically had masses 50 to 500 times greater than our Sun. Massive stars burn through their nuclear fuel with extraordinary speed. A star 100 times more massive than the Sun exhausts its fuel in just a few million years, then explodes as a supernova, scattering chemically enriched material into the surrounding gas. The next generation of stars formed from that enriched material, and each subsequent generation inherited progressively richer chemistry. Population 3 stars must have existed. Something had to create the first heavy elements. Every atom of carbon in every living organism on Earth, every atom of oxygen in every breath, every atom of iron in every blood cell was forged inside a star that lived and died before our solar system formed. But we have never directly observed a population 3 star. They lived too briefly and died too long ago. The only way to see them is to look far enough back in time, and even then we cannot see individual stars across billions of light years. We must look for the collective signature of many population 3 stars shining simultaneously within an early galaxy. Webb observations of a galaxy called GNZ 11, which existed 430 million years after the Big Bang, showed tantalizing hints. Spectra from the outer regions of this galaxy showed strong hydrogen emission with peculiar ratios between different spectral lines, ratios that match theoretical predictions for regions where population 3 stars are forming and ionizing their surroundings. The evidence is not yet definitive. Other astrophysical processes can produce similar spectral features, but the possibility is exciting enough that large systematic surveys are now searching hundreds of early galaxies for the same signatures. If confirmed in even a fraction of these systems, it would represent the first direct detection of the universe's original stellar generation, the stars that first brought light to the cosmos and seeded all future chemistry. Meanwhile, Webb has been revealing the large-scale architecture of the early universe with unprecedented clarity. Matter in the cosmos is not spread uniformly. It is organized into a vast network called the cosmic web, a structure of dark matter filaments along which galaxies gather like beads on invisible strings. Where filaments intersect, massive galaxy clusters form. Between them lie voids, immense underdense regions containing very few galaxies. This structure emerged from tiny fluctuations in density that existed just after the Big Bang. Regions that were slightly denser than average attracted more matter through gravity, growing denser still over billions of years, while underdense regions continued to empty out. The cosmic web is the end state of that amplification process. Webb can map the cosmic web at distances and epochs where no previous telescope could reach. By measuring the redshifts of thousands of galaxies in specific patches of sky, astronomers can reconstruct where each galaxy sits in three-dimensional space and trace the filaments connecting them. These maps reveal that the cosmic web already existed in a recognizable form when the universe was less than 1 billion years old. Filaments were shorter and less massive than today. Galaxy clusters were just beginning to form at the nodes, but the basic hierarchical architecture was already in place. The universe was organized from a very early time. Dark matter makes up approximately 85% of all matter in the universe. It does not emit, absorb, or reflect light, making it invisible to any telescope. We detect it only through its gravitational effects on visible matter. The cosmic web is fundamentally a dark matter structure. Galaxies form where dark matter is densest, tracing the underlying dark matter distribution the way foam traces currents on the surface of the ocean. By mapping visible galaxies, Webb maps the dark matter distribution indirectly. This allows astronomers to test models of dark matter and refine the parameters governing how quickly large-scale structure forms. The galaxies within this early web are themselves deeply strange. Early universe galaxies are dramatically denser than their modern counterparts. They pack the same mass of stars into volumes 1,000 times smaller. Stars in these systems orbit in crowded, compact regions where stellar encounters may be common. Something must have puffed these galaxies up over cosmic time, transforming the compact, dense systems Webb observes at high redshift into the large, diffuse galaxies we see in the modern universe. Several mechanisms contribute to this expansion. When galaxies merge, their stars redistribute through gravitational interactions, and the merged system ends up larger and less dense than either parent. Repeated mergers over billions of years gradually decrease galaxy density while increasing size without proportionally increasing stellar mass. Feedback from supernovae and active black holes can drive gas outward, removing mass from the central regions and allowing the remaining stellar population to migrate to larger orbits. The dark matter halos surrounding galaxies also grow through accretion, and changes in the gravitational potential cause stars to drift outward. The transformation of compact early galaxies into modern diffuse ones is a consequence of all these processes acting over cosmic time. Measuring the expansion rate of the universe has occupied astronomers for decades, and Webb has become a central tool in this effort. The rate of cosmic expansion is described by a number called the Hubble constant, which specifies how fast galaxies recede from each other per unit of distance. The current value is approximately 70 kilometers per second per megaparsec, where a megaparsec equals approximately 3.3 million light-years. This means that for every additional megaparsec of distance, a galaxy recedes 70 kilometers per second faster. Two independent methods of measuring the Hubble constant have been in persistent disagreement for years. The first uses the cosmic microwave background, the faint glow of radiation left over from when the universe first became transparent 380,000 years after the Big Bang. The detailed pattern of temperature fluctuations in this radiation, measured with extraordinary precision by satellites, allows cosmologists to calculate how fast the universe should be expanding today. That calculation yields a Hubble constant of 67.4 kilometers per second per megaparsec. The second method measures the distance and velocity of nearby galaxies using standard candles, objects with predictable intrinsic brightness. Certain types of supernovae, called Type 1a, explode with consistent peak brightness and serve as reliable distance indicators. Combining distance measurements with velocity measurements yields a Hubble constant of approximately 73 kilometers per second per megaparsec. 6 kilometers per second per megaparsec. The gap sounds small. In practice, it is enormous because both measurements have been refined to precisions that make the discrepancy statistically overwhelming. This is known as the Hubble tension, and it has persisted despite decades of improvements to both methods. Webb was hoped by many astronomers to resolve the tension, perhaps by revealing a systematic error in one of the measurement approaches. Instead, Webb confirmed the supernova-based measurement. Using the largest and most precise dataset of nearby supernovae ever assembled, Webb arrived at 73 kilometers per second per megaparsec, in agreement with previous measurements made by the Hubble Space Telescope. The tension is real. Instrumental error is not the explanation. A separate Webb study used 3 completely independent distance measurement techniques simultaneously. Cepheid variable stars, whose pulsation periods reveal their true brightness. Red giant branch stars, which reach a consistent maximum brightness before transitioning to a new evolutionary phase. And carbon stars, chemically evolved stars with predictable near-infrared colors and luminosities. All 3 methods were applied to the same set of 10 galaxies, providing a powerful cross-check. The 3 approaches agreed with each other, yielding a Hubble constant of 70 kilometers per second per megaparsec. This value sits between the 2 conflicting measurements, suggesting the tension may be more complex than a simple binary disagreement. But it does not resolve the underlying mystery. Why does the early universe's prediction for the expansion rate differ from what the local universe actually shows? The leading explanations are unsatisfying in their vagueness. Perhaps dark energy does not behave in the simple way assumed by current models. Perhaps the universe contains an unknown component that affected its evolution during specific epochs. Perhaps our local cosmic neighborhood expands slightly differently from the global average. Or perhaps the discrepancy points toward genuinely new physics, a modification to general relativity, or the existence of early dark energy, a form of energy that was present in the early universe and then dissipated. Scientists are reluctant to invoke new physics without compelling evidence, but the Hubble tension may be leaving them little choice. Dark energy itself remains one of the deepest unsolved problems in physics. Discovered in the late 1990s through observations of distant supernovae, dark energy is the name astronomers give to whatever is causing the expansion of the universe to accelerate. Galaxies are not just moving apart. They are moving apart faster and faster. About 6 billion years ago, the expansion rate began increasing, driven by dark energy overcoming the decelerating influence of gravity. The acceleration has continued ever since, and its effects will become increasingly dramatic in the far future. The simplest explanation for dark energy is that it is a fixed property of space itself, an energy density that remains constant even as the universe expands. Einstein's equations of general relativity actually allow for this in the form of what Einstein called the cosmological constant. Under this interpretation, as the universe grows larger and contains more space, more dark energy appears. The total energy driving expansion increases continuously. This sounds like it violates conservation of energy, and in the ordinary sense it does. But in the context of general relativity, energy conservation works differently in an expanding spacetime, and the equations permit this behavior without contradiction. If dark energy is truly constant, the expansion will accelerate forever. Galaxies outside our local group of gravitationally bound galaxies will recede faster and faster, eventually moving away faster than light can travel across the expanding space between us and them. They will disappear beyond the cosmic horizon, permanently unreachable, invisible. The universe will become progressively darker and emptier as the stars of distant galaxies fade from our view, and our own local group gradually exhausts its star-forming gas over trillions of years. If dark energy is not constant but growing stronger over time, the acceleration could eventually become extreme enough to overcome not just gravity between galaxies, but the electromagnetic force holding atoms and molecules together. Under this scenario, called the Big Rip, the universe would end with the destruction of all structure, from galaxy clusters to individual atoms, shredded by an ever-accelerating expansion. Current measurements give no indication this will happen, but neither do they rule it out entirely. If dark energy weakens over time and eventually reverses, gravity could regain dominance. The expansion would slow, halt, and reverse. Everything in the universe would begin moving back together, accelerating toward a singularity in a mirror image of the Big Bang called the Big Crunch. Current data does not favor this scenario, and the evidence strongly suggests dark energy remains active and effective. But the uncertainty about dark energy's fundamental nature means the universe's ultimate fate remains genuinely unknown. Webb contributes to dark energy research by measuring the expansion rate at different cosmic epochs, using supernovae at various distances to trace how the expansion rate has changed over billions of years. These measurements, combined with data from other telescopes and experiments, are building a detailed picture of dark energy's history. So far, the measurements are consistent with dark energy being constant, but the precision needed to detect subtle variations is still being achieved. Future observations will narrow the constraints significantly. While astronomy grapples with questions on the scale of the entire cosmos, Webb has also been exploring objects at the opposite extreme of the distance scale. Alpha Centauri is the closest stellar system to our Sun, located just over 4 light-years from Earth. It contains 3 stars, Alpha Centauri A and B, which resemble our Sun in size and temperature, and Proxima Centauri, a small red dwarf. Proxima Centauri hosts at least 2 confirmed planets, one of which orbits in the habitable zone where liquid water could potentially exist on a rocky surface. Alpha Centauri A and B have been harder to survey. Their brightness overwhelms the faint signals from any planets around them. Webb changed the approach. Using its mid-infrared instrument and a specialized observing strategy designed to peer through the glare of a bright nearby star, astronomers detected a faint infrared source located approximately twice Earth's orbital distance from Alpha Centauri. The signal is consistent with a large planet, possibly a gas giant. The detection is tentative, and additional observations will be needed to confirm whether the signal comes from a genuine planet or from a background object or instrumental artifact. But if real, this would be our closest known planetary neighbor outside the solar system, orbiting the star system closest to our Sun. Even a cold gas giant at Alpha Centauri would be scientifically valuable. It would constrain models of planet formation in solar-type star systems and tell us about the architecture of the nearest planetary system beyond our own. Gas giants can host large moons, and some of those moons might be habitable. Jupiter's moon Europa and Saturn's moon Enceladus both harbor subsurface oceans kept liquid by tidal heating, even though they orbit far beyond the habitable zone for surface liquid water. If a confirmed gas giant at Alpha Centauri hosts similar moons, the nearest potentially habitable world beyond the solar system could be in the system right next door. Closer to home in terms of cosmic scale, Webb has been observing planet-forming disks around young stars in our galactic neighborhood, revealing the chemical environments in which planetary systems assemble. When a cloud of gas and dust collapses to form a new star, the material that does not fall directly onto the star forms a rotating disk surrounding it. Over millions of years, solid particles in this disk collide, stick together, and build the rocky and icy objects that eventually coalesce into planets. The composition of the disk determines the composition of the planets that form within it. Webb observed a young stellar system and detected something specific in the disk's outer regions: crystalline water ice. This is not the amorphous ice that forms when water vapor freezes rapidly in space. Crystalline ice has a regular molecular structure that requires either slow freezing or a period of warming that allows water molecules to arrange themselves into an ordered lattice. Finding crystalline ice indicates that the disk has experienced thermal processing, perhaps from shock waves generated by the forming star or radiation from the stellar surface. The presence of abundant water ice in the cold outer regions of the disk matters enormously for understanding planetary habitability. Rocky planets forming in the inner disk, close to the star, form in a region too hot for water ice to exist. They start out dry. Water can only arrive on these inner planets later, delivered by comets or asteroids that formed in the ice-rich outer disk and subsequently migrated inward. The crystalline ice Webb detected represents exactly the reservoir that could eventually supply water to inner rocky worlds through this delivery mechanism. Without ice reservoirs in the outer disk, dry inner rocky planets have no source of water. The detection of abundant ice confirms that many planet-forming disks have the raw material needed to supply water to potentially habitable worlds. Beyond water ice, Webb has detected other volatile ices in planet-forming disks, including carbon dioxide, methane, and ammonia. These molecules freeze at the temperatures found in the outer regions of disks surrounding young stars. The specific mixture of ices present determines what chemical building blocks are available when giant planets and icy bodies form in the outer disk, and what materials eventually reach inner rocky planets through later delivery. These observations connect the chemistry of star formation directly to the potential for life on planets that may form billions of years after the disk disperses. Throughout all of these diverse observations, Webb continues to push the distance record outward, finding galaxies from earlier and earlier epochs of cosmic history. When Webb's first science results were announced, the most distant confirmed galaxy had a redshift of 13.2, corresponding to a galaxy that existed just over 400 million years after the Big Bang. JADES pushed the record to 14.32. Subsequently, a galaxy was confirmed at redshift 14.5. A candidate appeared at redshift 16. If spectroscopic confirmation follows, that galaxy formed just 250 million years after the Big Bang. The record advances because Webb is still early in its operational life. The deepest observations require tens of hours of exposure time each. Not all candidate deep fields have been observed. As astronomers work through the data and refine their analysis techniques, fainter and more distant objects emerge. The frontier of Webb's observational reach lies somewhere around redshift 20, corresponding to the first 200 million years after the Big Bang. Beyond that point, the universe had not yet formed the first stars. Looking at redshift greater than 20 would mean observing the cosmic dark ages themselves, the era of neutral hydrogen before starlight began. Webb might detect faint emission from this neutral hydrogen, but it will not find galaxies where none yet existed. Between the current record at redshift 14 and the theoretical limit at redshift 20 lies a stretch of cosmic history that Webb is actively exploring. A period covering some of the most important events in the universe's first chapter. What remains unknown is substantial. The nature of dark energy is unresolved. The solution to the Hubble tension is unidentified. The identity of dark matter, which makes up most of the matter in the universe, remains unknown despite decades of experiments designed to detect it directly. The origin of the first supermassive black holes, including how they grew so massive so quickly in the early universe, is not fully explained by any current model. Population 3 stars, the first stellar generation, have not been definitively detected. The mechanism that reionized the universe is broadly understood, but not quantitatively resolved at the precision needed to distinguish between competing models. The internal structure of the interstellar medium has only begun to be mapped. Future telescopes will extend humanity's reach further. Larger ground-based observatories with adaptive optics systems that correct for atmospheric turbulence are under construction and will provide complementary observations at wavelengths where the atmosphere is transparent. Space-based concepts are being studied that would carry mirrors twice the size of Webb's, potentially resolving individual stars and galaxies at extreme distances and imaging galaxies from the first 100 million years of cosmic history. Gravitational wave detectors being planned for space would open the universe to observation in an entirely different form of radiation, revealing mergers of supermassive black holes at high redshift that no electromagnetic telescope can detect. Webb itself will continue operating for at least 10 years, possibly longer depending on fuel reserves and instrument longevity. In that time, it will conduct progressively deeper surveys, observe more transient events like gamma-ray bursts and supernovae at extreme distances, study more planet-forming disks, characterize more exoplanet atmospheres, and push steadily toward the epoch of the first stars. Every new observation has a real chance of revealing something unexpected. The track record so far makes that near certain. The universe waited 13.8 billion years to be examined at this level of detail. Now that the examination has begun, it is producing surprises faster than theories can absorb them. Galaxies formed earlier and larger than they should have. Black holes grew more massive and more rapidly than any model predicted. The expansion rate of the universe does not agree with itself, depending on how you measure it. The intergalactic medium has structure we did not know existed. The space between stars is organized by magnetic fields into layered architectures too fine for any previous instrument to resolve. These discoveries do not indicate that astronomy is broken. They indicate that astronomy is working. The models were too simple. The predictions were too conservative. The universe, as Webb is showing us, is richer and stranger and more complex than anyone predicted. What we are living through now is not the end of cosmological understanding. It is the end of comfortable cosmological assumptions and the beginning of something far more interesting. If this kind of exploration matters to you, and it should, consider subscribing. The questions Webb is asking and the answers it is beginning to find will define how humanity understands its own place in the cosmos for generations to come. The cosmos is not finished revealing what it is, and Webb has only just opened its eye. To fully appreciate what Webb has accomplished, it helps to understand not just what it found, but how it finds things, and why those methods represent such a radical departure from what came before. Every telescope that has ever been built on Earth or placed in orbit faces a fundamental constraint. It can only collect the light that arrives at its mirror or lens. The size of the collecting surface determines how faint an object can be detected. Larger mirrors collect more light. But even a large mirror cannot detect light that has been shifted to wavelengths its instruments cannot record. Hubble's primary mirror spans 2.4 meters. For visible light astronomy, this was transformative. Hubble revealed galaxies at distances that had been completely beyond human reach, captured detailed images of nebulae and stellar nurseries, and measured the expansion rate of the universe with unprecedented accuracy. But visible light occupies only a narrow slice of the electromagnetic spectrum, and the most distant objects in the universe are entirely invisible to visible light instruments. Their light has been redshifted so far that it no longer exists at visible wavelengths at all. Hubble looked at the nearby universe with extraordinary clarity and caught glimpses of the distant universe with great difficulty, but the true cosmic dawn was beyond its reach. Webb's primary mirror spans 6.5 meters, almost 3 times the diameter of Hubble's. The collecting area scales with the square of the diameter. Webb's mirror collects roughly 6.3 times as much light as Hubble's per unit time. Combined with the sensitivity of its cryogenically cooled infrared detectors and its location far from Earth's heat and interference, Webb's effective increase in capability for infrared observations of distant objects is not 6 times greater than Hubble's. It is closer to 100 times greater in many observing modes. Objects that would have required years of Hubble integration time to detect, if they could be detected at all, become accessible to Webb within hours. This difference in capability is not merely quantitative, it is qualitative. There is a threshold below which a telescope simply cannot detect an object regardless of how long it stares at it. Hubble could not detect the most distant galaxies Webb has now cataloged, not because it needed more time, but because those galaxies produce infrared radiation that Hubble's instruments recorded as nothing. They were invisible in principle. Webb sees them as clearly resolved sources within a single night of observation. The expansion of the observable universe that Webb represents is therefore not an incremental improvement. It is a step change, the crossing of a threshold that moves the frontier of human knowledge by hundreds of millions of years in cosmic time. The engineering behind this capability required solving problems that had never been solved before. The primary mirror could not be built as a single piece. At 6.5 meters in diameter, it would be impossible to fit inside any available rocket fairing. The solution was segmentation. 18 individual hexagonal mirror segments, each measuring 1.32 meters across, were designed to fold together for launch and then unfold in space with nanometer-scale precision. Each segment is made of beryllium, a lightweight metal with a low thermal expansion coefficient, meaning it changes size very little as temperature changes. In the extreme cold of deep space, this stability is essential. Temperature fluctuations that would cause other materials to expand and contract enough to distort the optical surface by fractions of a wavelength are minimized in beryllium. Each segment is then coated with a microscopic layer of gold, approximately 100 nanometers thick, because gold reflects infrared light with extraordinary efficiency. The alignment of the 18 segments had to be achieved after launch in space by adjusting actuators behind each segment that could position the mirror surfaces to within 1 nanometer of the intended shape. A nanometer is 1/1000th of a meter. Human hair is approximately 80,000 nanometers wide. The alignment precision Webb achieves is on a scale far smaller than any biological structure. This level of control was achieved using a technique called wavefront sensing and control, in which the telescope repeatedly images a bright star and analyzes how the light behaves to determine the precise position and tilt of each mirror segment. Over a period of several months after launch, engineers made thousands of adjustments, gradually bringing all 18 segments into alignment so precisely that the primary mirror functions as a single coherent optical surface. The instruments behind the mirror are equally remarkable. Webb carries 4 primary science instruments. The near-infrared camera, or NIRCam, serves as the primary imaging instrument and covers wavelengths from 0.6 to 5 micrometers. The near-infrared spectrograph, or NIRSpec, can simultaneously obtain spectra of up to 200 objects at once by using a microshutter array containing 250,000 individual shutters, each smaller than a human hair, that can be selectively opened or closed to isolate light from specific objects in the field of view. The mid-infrared instrument, or MIRI, covers wavelengths from 5 to 28 micrometers and must be cooled to -266 degrees Celsius, just 7 degrees above absolute zero, to avoid drowning the faint infrared signals from distant objects in thermal noise from the instrument itself. And the fine guidance sensor provides the precise pointing information needed to keep the telescope locked on targets with the stability required for long exposures. The combination of these instruments gives Webb an observational capability that extends from the near-infrared, where the earliest and most distant galaxies emit most of their light, all the way through the mid-infrared, where warm objects like protoplanetary disks, planetary atmospheres, and dust-shrouded star-forming regions emit most of their energy. This range of wavelength coverage is why Webb can simultaneously study the universe's most distant objects and the chemical composition of ice in a disk 1,000 light-years away. It is the same instrument in different modes, the same mirror collecting light of different wavelengths, revealing utterly different phenomena across the same fundamental observation. Spectroscopy is particularly central to what Webb accomplishes. When astronomers split light into its component wavelengths and analyzed the resulting spectrum, they read the chemical fingerprints embedded in that light. Every element produces specific spectral lines at specific wavelengths, emission lines when atoms release energy and absorption lines when atoms absorb energy from passing light. The pattern of lines is unique to each element, like a barcode. By analyzing these barcodes in the spectra of distant galaxies, Webb can determine what elements are present, in what abundances, and at what temperatures and densities. For the most distant galaxies, this means measuring the chemistry of the early universe, determining how quickly heavy elements accumulated in the first billion years and what conditions prevailed in the interstellar medium of the first galaxies. For planets orbiting other stars, spectroscopy serves a different but equally powerful purpose. When an exoplanet passes in front of its host star, the starlight that passes through the planet's atmosphere carries the absorption signatures of whatever molecules are present there. Different molecules absorb at different wavelengths. Water absorbs strongly in the infrared. Carbon dioxide has distinctive absorption features. Methane, ammonia, and other potential biosignature molecules each leave specific imprints. By comparing the spectrum of a star with and without the planet's atmosphere and the light path, Webb can determine what the atmosphere contains. This technique, called transmission spectroscopy, has been applied to dozens of exoplanets since Webb began science operations. The results have been scientifically rich. Webb detected carbon dioxide in the atmosphere of an exoplanet for the first time with certainty. It detected sulfur dioxide, a molecule produced by photochemical reactions from volcanic emissions, suggesting active volcanism on a world outside our solar system. It characterized the atmospheres of multiple planets in the TRAPPIST-1 system, a compact system of 7 roughly Earth-sized planets orbiting a small red dwarf star located about 40 light-years from Earth. The TRAPPIST-1 planets have attracted extraordinary interest because 3 of them orbit within the habitable zone of their star, the range of distances where liquid water could exist on a planetary surface under certain atmospheric conditions. Webb's observations of TRAPPIST-1 planets have already ruled out the existence of thick, Venus-like atmospheres on at least 2 of the outermost planets. A thick atmosphere would retain and redistribute heat, creating a more uniform temperature distribution across the planet. The observations showed a larger-than-expected temperature difference between the day side and night side of TRAPPIST-1c, suggesting it either lacks a substantial atmosphere or has an atmosphere very different from Earth's. These results narrow the range of possible atmospheric conditions and constrain what kinds of atmospheres the remaining TRAPPIST-1 planets might host. The most interesting of the habitable zone planets in this system, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, have not yet been characterized in the same detail. Future Webb observations are planned. Beyond the TRAPPIST-1 system, Webb is searching for signs of habitability in dozens of other planetary systems. The search for potentially habitable worlds is not simply a search for planets at the right distance from their star. It requires understanding the composition of planetary atmospheres, the presence or absence of water, the role of the host star's radiation in driving atmospheric chemistry, and whether the planet has retained an atmosphere at all against the stripping effects of stellar wind and radiation. Red dwarf stars like TRAPPIST-1 present particular challenges. They are smaller and cooler than the Sun, which means their habitable zones are much closer in, and planets in those zones experience intense stellar flares that could strip away atmospheric gases over billions of years. Understanding whether planets around red dwarf stars can maintain habitable atmospheres despite these conditions is one of the central questions Webb is equipped to address. The search for exoplanet atmospheres also has implications for the search for biosignatures. Biosignatures are chemical signatures that would indicate the presence of biological processes. On Earth, the simultaneous presence of oxygen and methane in the atmosphere is considered a potential biosignature because these 2 molecules react with each other and would quickly disappear in the absence of continuous replenishment. On Earth, photosynthetic life replenishes oxygen and biological decomposition replenishes methane. If both molecules were found simultaneously in an exoplanet atmosphere at significant concentrations, it would suggest something is continuously producing them, and life is one candidate. Webb is not currently capable of detecting oxygen or methane biosignatures in the atmospheres of Earth-sized planets around Sun-like stars. The signals would be too faint and the host star too bright relative to the planet. but for planets orbiting small red dwarf stars, where the contrast between planetary atmosphere and stellar brightness is more favorable, Webb is approaching the sensitivity needed. No confirmed biosignatures have been found. No clearly habitable world has been identified beyond Earth, but the tools to conduct that search now exist in a way they never did before Webb launched. The question of whether life exists elsewhere in the universe, which has been philosophical for most of human history, has entered the realm of experimental science. We have the instruments, we have the techniques, we have a growing catalog of targets. What remains is time, precision, and more observations. The connection between all of these observations, from the most distant galaxies to the nearest planetary systems, is the fundamental question Webb was built to explore. How did the universe evolve from an almost uniform state just after the Big Bang to the rich, complex, structured cosmos we inhabit today? That evolution required the formation of the first stars, which created the first heavy elements. Those heavy elements enabled the formation of planets. Planets orbiting stable stars in appropriate conditions could develop liquid water. And somewhere in that chain of events, at least once, chemistry became biology, and the universe became aware of itself. Webb does not search for life directly, but it explores every step in the chain of events that makes life possible. It finds the first galaxies. It observes the first massive stars exploding and scattering heavy elements. It watches planetary systems assembling from ice and dust. It characterizes the atmospheres of worlds that might, in some cases, harbor the conditions for biology. Each observation is a link in a chain of understanding that, when complete, will tell us whether we are alone or one of many. That understanding is not complete. It may never be complete within a single human lifetime. The universe is 13.8 billion years old and incomprehensibly vast. The observable universe extends 46 billion light-years in every direction, a sphere of space so large that light from its edge has been traveling since before the Earth existed and has only recently arrived. And the observable universe is only the fraction of the total universe that light has had time to reach us from. The true extent of everything that exists may be infinitely larger, filled with galaxies and stars, and possibly life that we will never observe because the light from those regions will never reach us in the finite age of the cosmos. Within that immensity, the James Webb Space Telescope has access to a specific region and a specific slice of cosmic time. It can observe objects up to a certain redshift, a certain distance, a certain age. It cannot see behind the cosmic horizon. It cannot detect objects too faint for even its extraordinary sensitivity. It cannot observe wavelengths outside its instrument range. It cannot survive damage to its sunshield or its mirrors or its instruments. It is a machine, built by people, subject to mechanical limits and fuel constraints and the finite operational lifetimes of its cryogenic cooling systems. And within those limits, it has already shown us more than anyone expected. It found galaxies too old and too large for their age. It found black holes too massive for their host galaxies. It found a black hole merger from when the universe was less than 1 billion years old. It found supernova explosions from the era when the first stars were dying. It found the internal structure of interstellar clouds at scales hundreds of times smaller than previously resolved. It found water ice in the disk of a young star-forming system. It found a tentative signal suggesting a planet around our nearest stellar neighbor. It is refining our measurement of the expansion rate of the universe. It is mapping the distribution of galaxies at cosmic dawn. It is searching for the spectral signatures of the first stellar generation. All of this within its first few years of operation. The next years will push further. Deeper surveys will find galaxies from earlier epochs. Better spectroscopic analysis will characterize more exoplanet atmospheres. More light echoes will map more of the interstellar medium. More gamma-ray burst afterglows observed in the early universe will build statistics on massive stellar death at cosmic dawn. More little red dots will have their spectra analyzed and their properties constrained. more lensed galaxies behind massive clusters, will be resolved to the level of individual star clusters, showing us the building blocks of the first large galaxies in unprecedented detail. What Webb will ultimately find, what its complete archive of observations will show when astronomers have spent decades analyzing every spectrum and every image, cannot be predicted. That is precisely the point. The history of astronomy is a history of the universe refusing to behave the way we expected, and of instruments capable of detecting that refusal, teaching us something genuinely new. Every time the boundary of observational capability has expanded, something unexpected has been found. The cosmic microwave background revealed the uniformity of the early universe. Hubble showed that the universe is expanding. The discovery of distant supernovae revealed that the expansion is accelerating. Gravitational wave detectors heard the collision of black holes and neutron stars. Webb is revealing the earliest structures, the oldest stars, and the chemistry of worlds around other suns. Each of these discoveries changed what we thought we knew. The Webb discoveries are still in their early phase. The instrument is operating. The data is flowing. The analyses are being published week by week. We are living through the observations, not looking back at them from a future where their implications are fully understood. The full meaning of what Webb is finding, what it implies about the formation of galaxies, the growth of black holes, the possibility of life, the nature of dark energy, and the fundamental parameters governing the universe, will take years and decades to absorb and integrate into a new synthesis. What is clear even now is that the universe is not the simple place that our models assumed. It formed structure earlier than predicted. It grew black holes faster than theory allowed. It organized its matter into galaxies at cosmic dawn in ways that required conditions and processes not yet fully accounted for. It contains forms of matter and energy, dark matter and dark energy, that remain completely unidentified despite constituting 95% of everything that exists. It is expanding in a way that different measurement approaches do not agree on, and it may, in some of its billions of planetary systems, harbor phenomena far stranger and more interesting than any galaxy or black hole. The James Webb Space Telescope will not answer all of these questions, but it is asking them with unprecedented precision, and its answers are making the questions more specific and the path toward understanding clearer. Every observation is a vote cast by reality against or in favor of a particular theory. And reality, as Webb is demonstrating week after week, consistently votes in surprising ways. The universe waited 13.8 billion years to be seen this clearly. And what it shows us, now that we are finally looking, is that it has been far stranger, far more complex, and far more remarkable than we had the instruments to know. Understanding just how extreme the scale of what Webb is probing requires stepping back from individual discoveries and looking at the sheer scope of cosmic time. The universe is approximately 13.8 billion years old. Earth is approximately 4.6 billion years old. The first multicellular life on Earth appeared roughly 600 million years ago. The first anatomically modern humans appeared around 300,000 years ago. Written human history spans approximately 5,000 years. The entire span of recorded civilization represents less than 1/millionth of the age of the universe. When Webb observes a galaxy at redshift 14, it is looking back to when the universe was 290 million years old. That is the age of the universe when jades existed. 290 million years. For context, 290 million years ago on Earth, the age of the dinosaurs had not yet begun. The first mammals would not appear for another 50 million years. The continents were arranged completely differently. The oceans were different. The atmosphere had a different composition. The organisms that would eventually give rise to humanity did not yet exist in any recognizable form. And yet the universe was already building galaxies, already igniting stars, already, possibly, forming rocky planets around some of those stars. The processes that would eventually produce a planet capable of hosting observers, capable of building telescopes, capable of looking back at those early galaxies, were already operating 13.5 billion years ago. The chain of events is unbroken from those first luminous structures to the moment you are encountering these words. Every atom in every cell of every organism on Earth was processed through stellar interiors that lived and died in the billions of years between the universe's first galaxies and the formation of our solar system. We are, in a genuinely literal sense, descendants of those first stars. The spectral observations Webb conducts of early galaxies sometimes show the chemical signatures of elements heavier than hydrogen and helium in systems that existed just a few hundred million years after the Big Bang. This means that stars had already lived and died in those systems before Webb's earliest observable epoch. Stars massive enough to create heavy elements through nuclear fusion and scatter them through supernova explosions have lifetimes of only a few million years. If Webb can detect heavy elements in a galaxy from 500 million years after the Big Bang, those heavy elements were created by stars that lived and died within the first few hundred million years. Stars we cannot see directly because they existed before even Webb's earliest detectable galaxies. This is what population 3 stars represent in the cosmic narrative. They are the invisible ancestors, the first generation, the stars that seeded everything that followed with the atoms needed for chemistry, for geology, for biology. Every search for their spectral signatures is a search for the beginning of the chain of events that leads to us. Finding them, even in the form of hints in a distant galaxy spectrum, would be one of the most profound scientific discoveries in the history of human observation. It would mean we can see the first generation of stars our universe produced, the very first stellar fires, the engines that broke the dark ages and began the long process of building a universe capable of complexity. What makes the galaxy GNZ 11 particularly interesting as a candidate for population 3 star signatures is not just that it shows anomalous spectral features, but that it exists at a time when population 3 stars should still be present. This galaxy formed 430 million years after the Big Bang. The very first stars may have ignited within the first 100 to 200 million years after the Big Bang. Population 3 stars with masses of 100 solar masses would live for only about 3 million years before exploding. But population 3 stars at the lower end of the predicted mass range, around 50 solar masses, might live for 4 to 5 million years. And in a galaxy that has been forming stars continuously since very early in cosmic history, new population 3 stars might continue forming from pockets of pristine, unenriched gas that somehow survived the early enrichment process. GNZ 11 shows hints of exactly this scenario in specific spatial regions of the galaxy, the outer regions, where pristine gas might persist, while the inner regions have already been enriched by earlier stellar generations. The galaxy JADES GSZ 14-0, JADES, adds another dimension to this picture. Its extraordinary brightness and large size, given its age, suggest it was forming stars at rates that would have produced significant numbers of the most massive stellar generations in its first tens of millions of years. Those massive stars would have lived and died rapidly, enriching the galaxy's gas with heavy elements and simultaneously exploding as supernovae that heated the surrounding interstellar medium. The signatures of this rapid chemical enrichment should be visible in JADES' spectrum, and Webb has begun to detect them. The galaxy shows evidence of elements heavier than hydrogen and helium despite existing less than 300 million years after the Big Bang. The enrichment happened fast. The stars that produced it lived and died in a cosmological eye blink. The supernova remnant observations Webb has enabled tell a parallel story. When a massive star dies, it does not simply disappear. The explosion sends a shockwave outward through the interstellar medium at velocities of thousands of kilometers per second. This shockwave sweeps up surrounding gas and dust, compresses it, heats it to millions of degrees, and causes it to glow across a wide range of wavelengths. Over hundreds of years, this shockwave expands into a cavity called a supernova remnant. As the remnant expands, it gradually slows as it accumulates more swept-up material. Eventually, the shockwave slows to speeds comparable to the surrounding gas, and the remnant fades and disperses back into the interstellar medium, enriched now with the heavy elements scattered by the explosion. The Cassiopeia A supernova remnant is the shattered remains of a star that exploded in the 1600s, just beyond the age of recorded telescopic observation. It sits approximately 11,000 light-years from Earth and represents one of the best-studied supernova remnants in the sky. Webb has observed its surroundings in extraordinary detail, using the light echo technique to illuminate interstellar material that the explosion's light pulse is only now reaching. The structures revealed in that material, the sheets and layers organized by magnetic fields, represent the conditions into which future stellar generations will form. The heavy elements scattered by the explosion that created Cassiopeia A are already beginning to seed the next cycle of star formation in the surrounding region. This cycle has been operating for the entire history of the universe. Stars form from interstellar gas and dust. They live for millions to billions of years, synthesizing heavy elements in their cores through nuclear fusion. They die, scattering those elements into the surrounding medium through stellar winds and supernova explosions. The enriched gas mixes with surrounding material. Eventually, it cools and collapses to form a new generation of stars. Those stars begin the cycle again, now with a slightly richer chemical inventory than their predecessors. Our own solar system is the product of this cycle, operating over approximately 4.6 billion years of cosmic history. The Sun is a third-generation star, meaning it formed from material that had been processed through at least 2 previous generations of stellar evolution. The carbon, oxygen, nitrogen, iron, calcium, phosphorus, and all the other elements that make up the bodies of living organisms on Earth were created inside stars that lived and died before the solar system formed. A supernova explosion approximately 4.6 billion years ago injected fresh heavy elements into the cloud of gas and dust that would become the solar nebula, triggering its collapse and potentially providing the radioactive isotopes that heated the early Earth's interior and drove the geological processes that made our planet active and dynamic enough to sustain life. Webb is not just studying the universe at cosmic distances. It is tracing the history of the atoms that make us. When it observes a gamma ray burst in the early universe and detects silicon, oxygen, and iron in the spectrum of the dying star's ejecta, it is watching the production of the same elements that form the bones and blood of every organism that has ever lived on Earth. When it detects crystalline water ice in a planet-forming disk, it is watching the accumulation of the molecules that will eventually become the oceans and atmosphere of a world that might, billions of years from now, harbor life. When it observes the internal structure of interstellar clouds shaped by magnetic fields into layered sheets, it is mapping the environment inside which new stars and new solar systems will eventually ignite. The universe is not a collection of separate phenomena observed by a separate observer. Every object Webb studies is connected to every other through the flow of matter, energy, and information across cosmic time. The first galaxies produced the first heavy elements. Those elements eventually enabled the formation of rocky planets. Rocky planets in appropriate conditions could develop liquid water. Liquid water enables complex chemistry. Complex chemistry, under the right conditions and over sufficient time, can become biology. And biology, continuing over billions of years of evolution, can eventually produce minds capable of building telescopes and looking back at the universe's beginning. The fact that we can do this, that we can build a machine, send it to a stable point in space 1,000,000 miles from Earth, unfold it with nanometer precision, cool its instruments to within 7 degrees of absolute zero, and then use it to detect photons that have been traveling through an expanding universe for more than 13 billion years, is itself a consequence of all the stellar generations that preceded our own solar system. We are made of stardust looking at stars. We are the universe observing itself, using instruments built from the heavy elements forged in the stellar generations that made us possible. This is not philosophy. It is astrophysics. Every measurement Webb makes is a measurement of the processes that led, through an unbroken chain of physical events, to the observers taking those measurements. Understanding the first galaxies is, in a real sense, understanding our own origin. Understanding population, 3 stars, is understanding the beginning of the chain of stellar generations that culminated in the Sun. Understanding the formation of planetary systems is understanding how a world like ours came to be. Understanding the atmospheres of exoplanets is expanding the domain of the question of whether this chain of events that led to us is unique or common. Webb does not answer these questions definitively. It advances them. It narrows the uncertainties. It reveals what was previously invisible. It turns philosophical speculation about the universe's nature into specific, quantitative measurements that either confirm or refute specific physical models. This is what science does. And what Webb is doing is science at its most ambitious and most consequential scale. The telescope has a finite operational lifetime. Fuel for the precise station-keeping maneuvers that keep it at the second Lagrange point was limited at launch. Engineers estimated enough fuel for at least 10 years of science operations, with the possibility of extending that timeline if operations are conducted efficiently and no anomalies require excessive fuel expenditure. The initial trajectory to the second Lagrange point was executed so precisely that significantly less fuel was consumed than anticipated, which extended the expected mission lifetime. Current estimates suggest Webb may operate well beyond the initially planned 10-year mission. But eventually the fuel will run out, and without the ability to maintain its orbital position, the telescope will drift away from the Lagrange point and lose its operational geometry. In the time it has, Webb will continue accumulating observations at a pace limited by the finite number of hours in each year and the competing demands of thousands of approved science programs. The Hubble Space Telescope, by comparison, has been operating for more than 3 decades, and its archive continues to generate new scientific publications every year. Webb's archive will similarly accumulate value over time, providing a reference dataset that astronomers will mine for discoveries long after the telescope's active operations cease. Data from Webb's first years of science observations is already generating publications at an extraordinary rate. The cumulative impact of a decade or more of operations will be difficult to overstate. What comes after Webb in the long-term future of astronomical observation depends on decisions not yet made and technologies not yet matured. Ground-based observatories currently under construction, including the extremely large telescope being built in Chile's Atacama Desert, will carry mirrors 39 meters in diameter. These telescopes will collect vastly more light than any existing observatory and will operate with adaptive optics systems that correct for the blurring effects of Earth's atmosphere in real time. For certain types of observations, particularly those requiring extremely high spectral resolution or access to specific wavelength ranges where the atmosphere is transparent, these ground-based giants will complement and sometimes surpass space-based observatories. But they cannot observe in the mid-infrared, where Earth's own thermal emission drowns out faint astronomical signals, and they cannot escape the turbulence and absorption of the atmosphere entirely. For the kind of deep infrared surveys of the early universe that define Webb's most transformative contributions, the future requires space. Concepts for the next generation of space-based observatories include the Habitable Worlds Observatory, a proposed mission designed specifically to directly image Earth-like planets around nearby Sun-like stars and characterize their atmospheres. This mission would require a mirror larger than Webb's, a coronagraph capable of blocking enough starlight to reveal planets orbiting 10 orders of magnitude fainter than their host stars, and an instrument suite capable of detecting the spectral signatures of oxygen, water, methane, and other potential biosignature molecules. It would not launch until the 1940s at the earliest under current planning scenarios. Other proposals envision even larger space observatories optimized for cosmological observations, with mirrors spanning 15 to 20 meters and capable of obtaining spectra of galaxies at redshifts approaching 25, pushing into the epoch of the very first stars. These are concepts, not funded missions. The path from concept to launch requires decades of technology development, engineering demonstration, political will, and funding continuity. But the scientific case is clear, and the technology trajectory, though challenging, is not fundamentally impossible. The universe has more to show us than any existing or planned observatory can see. In the meantime, Webb continues its vigil at the second Lagrange point, staring into the infrared universe with perfect patience. It does not tire. It does not blink. It records photon by photon, spectrum by spectrum, the light of a cosmos that has been sending its history outward in all directions since the first stars ignited. That history is arriving at Webb's mirror continuously. Photons that have been traveling for billions of years completing their journeys at the rate of Webb's observing schedule, transformed by its instruments from raw light into data that human minds can analyze and interpret and argue about and understand. The universe does not care whether we understand it. It does not adjust its behavior to fit our models or slow its evolution to match our observing schedules. It simply is what it is, operating according to physical laws that appear to apply consistently across the entire observable cosmos and across all of cosmic time. The fundamental physics that governed the formation of the first galaxies is the same physics that governs the formation of planetary systems around young stars in our galactic neighborhood. The same gravitational dynamics that drove the early cosmic web to develop its current structure are operating in the gas clouds that will eventually collapse to form the next generation of stars in the Milky Way. The same nuclear physics that powered population 3 stars powers the Sun today. This universality of physical law is itself one of the most profound observations astronomers have made. Webb's observation of an ancient supernova that looks nearly identical to modern supernovae is a confirmation that the laws of physics do not change over cosmic time. The speed of light is the same. The charge of the electron is the same. The gravitational constant is the same. Across 13 billion years of cosmic history and tens of billions of light years of cosmic distance, the universe plays by consistent rules. This consistency is what makes astronomy possible. Without it, measurements of distant objects would tell us nothing reliable about the underlying physics. With it, a photon from a galaxy at redshift 14 carries information that can be interpreted using the same physical laws we test in laboratories on Earth. The questions that Webb cannot answer, the questions that will occupy the next generation of astronomers and physicists and instruments, are equally profound. Why does the universe have the specific laws it has? Why do the constants of nature have the values they do? Why is the universe so uniform on large scales despite the random quantum fluctuations that generated the seeds of all structure? Why is there matter rather than antimatter? What is dark matter made of? What is the fundamental nature of dark energy? Are the laws of physics truly universal, or do they vary across regions of space too distant to observe? Does the observable universe represent the totality of existence, or is it a small bubble within a larger multiverse of other regions with different properties? These questions may or may not be answerable with any conceivable observation. Some may be fundamentally beyond empirical reach. Others may yield to future instruments and methods not yet imagined. But Webb's contributions are ensuring that the next generation of questions is more specific, more constrained. and more directly connected to observable reality than the questions that preceded them. That is how science advances, not by answering everything, but by answering enough to know what the most important remaining questions are, and by building the tools that make those questions answerable. The James Webb Space Telescope is one of those tools, possibly one of the most important scientific instruments humanity has ever built. Its discoveries will continue accumulating for as long as the telescope remains operational, and for decades afterward as the data archive is reanalyzed with new techniques and new understanding. The story of what Webb finds is not finished. It is barely begun. And the universe, vast and ancient and indifferent and extraordinarily beautiful, will keep sending its history outward at the speed of light for as long as there are instruments capable of receiving it. One of the most underappreciated aspects of Webb's operation is how it manages to observe so many different types of objects with a single instrument system. The universe does not neatly separate itself into categories. The same telescope that must peer at galaxies from the universe's first few 100 million years must also characterize the atmosphere of an exoplanet 40 light-years away with sufficient precision to detect the spectral signatures of individual molecules. The same mirror that collects ancient infrared photons redshifted from ultraviolet by 13 billion years of cosmic expansion must also separate the faint thermal emission of a protoplanetary disk from the overwhelming brightness of the young star at its center. Managing these enormously different scientific requirements within a single instrument required prioritization, compromise, and extraordinary ingenuity. The solution was modularity. Each of Webb's 4 primary instruments occupies a distinct region of infrared wavelength space and serves distinct scientific purposes, but they share the same primary mirror and secondary mirror system. Light from the sky falls onto the primary mirror, reflects to the secondary, which is suspended by support structures above the primary, and then passes through a hole in the center of the primary to the instrument module behind. There, a series of mirrors and beam-splitting optics route the light to whichever instrument is active. Multiple instruments can potentially receive light simultaneously in some configurations, though the typical mode is to operate one instrument at a time with the others in standby. The scheduling of Webb observations reflects the extraordinary competition for its capabilities. Astronomers around the world submit proposals to observe specific targets for specific science goals, and an independent panel reviews thousands of proposals and awards observing time based on scientific merit, feasibility, and the overall balance of the science program. The telescope is oversubscribed by factors of 5 to 10 or more in most cycles, meaning for every hour of telescope time available, 5 to 10 hours of scientifically compelling proposals compete. The science that gets done with Webb is therefore a selection from an even larger universe of science that could in principle be done if the telescope had more time. This competitive selection ensures that the observations Webb makes represent the highest priority science identified by the global astronomical community. When Webb discovers something unexpected, as it has repeatedly in its first years of operation, the community rapidly responds by submitting new proposals to follow up the discovery, and the allocation system accommodates urgent or time-sensitive observations through a director's discretionary time mechanism. This flexibility has allowed Webb to respond to transient events like gamma-ray bursts within hours of their detection, and to follow up on surprising discoveries quickly enough to inform subsequent analysis. The data Webb collects flows through a pipeline of processing and calibration before it reaches the scientists who propose the observations. Raw detector readouts must be corrected for instrumental effects, calibrated against known sources, and formatted into standard data products that can be analyzed using standard software tools. This pipeline was developed over years before launch and continues to be refined as astronomers learn more about the telescope's actual on-orbit performance. Early in the mission, Updates to the calibration pipeline improved the sensitivity and accuracy of Webb measurements, effectively increasing the telescope's scientific output without any change to the hardware itself. Public data from Webb observations becomes available to the global scientific community after a proprietary period that ranges from a few months to a year, depending on the terms of the original observing program. This policy ensures that the proposing astronomers have time to publish their results, while also maximizing the long-term scientific return of the archive by making data widely accessible. Astronomers who had no involvement in the original observations can and do find new discoveries by reanalyzing Webb data with different techniques or looking for different objects than the original program targeted. This model of shared astronomical archives is one of the most productive features of modern big telescope astronomy. The Hubble Space Telescope archive has generated more scientific publications per year in recent years than it did in its early operational period, because more astronomers have learned to use the data and more scientific questions have been developed that the archive can address. Webb's archive will similarly accumulate value over decades, providing a reference dataset of unprecedented depth and wavelength coverage that will serve scientific purposes not yet imagined. For the next few years, Webb's most productive work will continue to span the full range of cosmic phenomena it can observe. Early universe galaxies will be found at progressively earlier epochs as deeper surveys are conducted. The properties of galaxy populations will be characterized more completely as the sample of well-studied high redshift galaxies grows from dozens to thousands. The timeline of reionization will be mapped with increasing precision as spectroscopic surveys probe the ionization state of the intergalactic medium at different redshifts. The origins of the first supermassive black holes will be constrained as more examples of overmassive black holes at high redshift are found, and their properties compared against theoretical models. The fate of the earliest massive stars will be traced through the chemical enrichment they produced in the earliest galaxies. Closer to home, Webb will continue characterizing the atmospheres of exoplanets and searching for the closest analog to Earth's conditions that current technology can reach. It will observe more protoplanetary disks and map the chemical inventories of planet-forming environments around stars of different masses and ages. It will study stellar nurseries in the Milky Way and nearby galaxies with the infrared vision that penetrates dust clouds and reveals the earliest stages of stellar development. It will watch stars dying in our galactic neighborhood with the spectral precision to measure the detailed chemistry of their deaths. The cosmic story Webb is telling is not a single narrative with a beginning, middle, and end. It is an interlocking web of processes operating simultaneously across every scale of space and time, from the subatomic quantum fluctuations that generated the initial density variations in the early universe to the 10 billion light-year filaments of dark matter that define the universe's largest structures. Webb observes these processes at every scale it can access, building a picture of cosmic history that no single observation program, no single wavelength range, and no single generation of astronomers could complete. What drives all of it, ultimately, is the same force that has driven every scientific advance in the history of human civilization: curiosity, the desire to know what is out there, the refusal to accept incomplete answers when better instruments might provide more complete ones, the recognition that the universe is under no obligation to conform to our expectations, and that the moments when it surprises us, when observations contradict models and force the revision of theories that seemed well established, are the most scientifically valuable moments of all. Webb is producing those moments regularly. It will continue to do so for as long as it operates, and the astronomers analyzing its data, arguing over its implications, and using its discoveries to formulate the next generation of questions. are participating in a tradition of inquiry that connects them to every observer who has ever pointed an instrument at the sky and wondered what they were seeing. The universe is old, it is vast, it is strange, and we are improbably here to look at it. That we can look at it with the precision and depth of the James Webb Space Telescope, across 13 billion years of cosmic time and to distances that dwarf anything human imagination could have conceived before the era of modern science, is one of the most remarkable facts about the situation we find ourselves in. The light is still arriving, the observations will continue, and whatever Webb finds next, it will change what we think we know. The specific instruments aboard Webb each carry their own story of engineering achievement. The near-infrared spectrograph represents a particular triumph. Before any telescope existed that could obtain spectra of hundreds of objects simultaneously, astronomers had to observe objects one at a time, making large statistical surveys of distant galaxy populations extraordinarily time-consuming. Webb's NIRSpec uses a system of 250,000 individually addressable microscopic shutters, each about 100 micrometers wide, arranged in a grid called a microshutter assembly. Before an observation, scientists program specific shutters to open, precisely targeting the positions of selected objects while leaving the rest closed. This allows light from up to 200 individual objects to enter the spectrograph simultaneously, each entering through its designated shutter.